Welcome to all for learning session 50. In previous session we learned acidic properties of alcohols, with which type of reagents alcohols are going to react, means alcohols are showing acidic properties, and with which type of reagents alcohols are not showing acidic properties, we was learned. Let us continue for that. Acidic properties of alcohols. Here I am going to consider prop 2 ion 1 mole. This prop 2 ion 1 mole, which has 2 acidic hydrogens, alcoholic hydrogens is acidic, and this triple bond carbon containing hydrogen also acidic. That means in process there are 2 acidic hydrogens, which upon treatment with base need to abstract proton. Let us suppose we are using one equivalent of base. We are using only one equivalent of base. In such a case, it abstracts proton from this oxygen rather than this carbon. As we learned in previous session, acidic nature of this alcohol is the alcoholic hydrogen is more than carbon containing hydrogen, triple bond carbon containing hydrogen. Obviously, base abstracts proton from this oxygen. We are getting alkoxide. If we are using further one equivalent of base, now obviously this hydrogen is going to abstract. So you are getting negative charge here. That means by consuming 2 equivalents of a base, we are getting dianion, where oxygen bear negative charge and here carbon bear negative charge. Now this one upon treatment with ethyl iodide, which one is going to participate in the reaction? Listen, either possibility here oxygen may has to participate in the reaction, oxygen may participate in the reaction, or carbon may participate in the reaction. That means carbon may act as a nucleophile or oxygen containing negative charge acts as a nucleophile. This reaction what we call the SN reaction, nucleophilic substitution reaction. There are 2 possibilities, either oxygen may behave as nucleophile or carbon may behave as a nucleophile, either of these 2. But when we are using here only one equivalent of ethyl iodide, then which one is going to participate first here? The anion which formed last reacts first. The anion which formed last, that reacts first. Why like that? Why anion which formed last has to react first? Because of this one, as we mentioned that first this hydrogen is going to abstract. That means out of these 2 hydrogens, this hydrogen is more acidic. That means its conjugate is weak base, being weak base, weak nucleophile. And here this carbon containing, triple bond carbon containing hydrogen is more acidic nature it has. Being it has more acidic nature, obviously compared to OH, this one is less. Of course more acidic, but compared to this hydrogen is more acidic. But compared to this hydrogen is less acidic. It's clear. So out of these 2, this one is more acidic, means its conjugate is a weak base. And this one is less acidic, its conjugate is strong base. So being strong base, obviously its nucleophilicity is more. Here this one preferably attacks upon ethyl iodide, means this one is going to participate in SN reaction. Of course this is SN2 reaction and bimolecular nucleophilic substitution reaction. SN2 reaction here. Here SN2 reaction, what happened? Carbon-carbon bond formed, but instead of that, oxygen-carbon bond, means a newly formed bond is carbon-carbon bond. Further acidification, we are getting again X means earlier 3 carbon containing alcohol, now it converts into 5 carbon containing alcohol. 3 carbon containing alcohol converts into 5 carbon containing alcohol. So directly, instead of doing all these things, directly if we are using one equivalent of base and further ethyl iodide, then what happened product? If this one upon treatment with ethyl iodide, you are getting product here OC bond instead of CC bond, CCH2 OC2H5. So you can prepare directly like this. But if you want to replace this hydrogen with alkyl group, then we have to use first excess of base and followed by SN reaction with ethyl iodide, then you are getting this product. Hope you got the first reaction. Let's come to second one. Here both the carbons are triple bond carbons and triple bond carbon containing hydrogen is acidic as we know earlier. So here what we are expecting when we are using two equivalents of butyl lithium, which is organometallic compound. From here you are getting carbanium, butyl carbanium. And this carbanium is strong base. Being strong base, it abstracts proton. Because of we are using two equivalents here, it can abstract proton from both the carbon atoms. Then we are getting this product. That means C minus and Li plus. C minus and Li plus. This one upon treatment is further butyl lithium. After abstraction of these two hydrogens, there is no more hydrogen here, triple bond carbon containing hydrogen. But here hydrogens are sp3 carbon containing hydrogens. As we know, these hydrogens are much less acidic, and because of this carbon is attached to sp hydrogen carbon, this carbon containing hydrogens are little bit acidic in nature. When we are using butyl lithium, this butyl carbanium as going to abstract proton from this carbon, you are getting negative charge. This one upon treatment with epoxide, ethylene epoxide, as the same principle, anion formed first, anion formed last, reacts first. Out of all these negative charges, which one formed last here? This one. And this one is going to take part in SN reaction, nucleophilic substitution reaction. Here also, it is a bimolecular. This carbanium has to come and attack upon this carbon, and these electrons CO bond electrons are shifted towards oxygen. Then there will be a new CC bond formation takes place in between these two carbon atoms. Then we are getting Li plus C minus remains as such here and here both terminals. And this carbon containing negative charge is going to form bond with this carbon CH2O minus, which upon protonation you are getting these two hydrogens as such, and this O minus also going to convert into OH. So looks like these two hydrogens only has to replace, but this hydrogen we cannot expect that. But one is giving three equivalents of butyl lithium. Out of three equivalents, two equivalents are going to abstract proton from these two carbon atoms, and when we are using third equivalent, that third equivalent is going to abstract either of these two hydrogens because both hydrogen atoms are in the same environment. So we are getting carbanium, which is the lastly formed carbanium. This lastly formed carbanium is this one. This one is going to participate in reaction first rather than the first two carbanions. Hence, there will be new CC bond formation takes place with respect to this carbon, with respect to this carbanium, but not either of these two carbanions, right? And which upon acidification we are getting product like this. So directly can we replace that hydrogen? No possibility here. So let us come and discuss the third one. Here in third one, there are two OH groups. Here, earlier case, two different hydrogens are there, of which less reactive or less acidic hydrogen from that carbanium, less acidic hydrogen, after abstraction of the hydrogen, the carbanium got formed here, that carbanium is going to take part in the reaction. But here in this case, both are OH groups. So of this, how can you distinguish? It means I want to prepare only this oxygen contain, means substitution need to take place at this oxygen. Means I want to see that reaction by participating this oxygen only rather than this oxygen. I don't want to see this one. I want to see this OH group has to take part in the reaction. So for that, I'm doing acylation first. So during acylation, OH acylation takes place. OH group is going to convert into OC double bond OCH3. Here also OC double bond OCH3. But here, if you observe, even though both are OH groups, this hydrogen OH group containing carbon is more hindered. Here, P double bond O PH means diphenyl phosphorus group is there. So which causes more hindrance, and this one is less hindered one. Being less hindered one, it is more reactive. It is more reactive. If I want to prepare a monoacylation product, means only one OH group has to take part in the reaction. So in such a case, because of this OH group is less hindered, means more reactive. Being more reactive OH group, obviously its tendency to participate in acylation will be more. If you want to form OH acylated product from this OH, that is very easy. Whereas from this OH, it's quite difficult because of it is less hindered. Sorry, more hindered and less reactive. That means here you cannot prepare this OH group containing acylation product major. You are getting by participating this OH group in acylation product major. You are getting this product acylation major and this one acylation is minor. But I want to prepare this OH group participating in acylation product will be major. I want to get that. So for that, what I am doing here, I am going to make first acylation by using acetic anhydride or acid chloride, whatever it may be, excess. When we are using excess, obviously both the OH groups are going to participate in acylation and OH is going to convert into OC double bond OCH3 like this. So once OC double bond OCH3 formation takes place, later I am going to use again base by using K2CO3, aqueous K2CO3 and methyl alcohol at 20 degrees Celsius. When we are using aqueous K2CO3 and methyl alcohol at 20 degrees Celsius, what happens here? Nothing but OH minus produces because of CO3 2 minus undergoes hydrolysis and furnishes OH minus ions. That OH minus ions are going to replace this OCOCH3 group. Because this one is less hindered again. So being less hindered, which will be replaced by OH group, then we are getting OH. So final product, more hindered acylation takes place. If you make directly acylation, you are getting less hindered one. Instead of that, what I use here, I am doing acylation first thoroughly. All the OH group got acylated. Later I am going to use base, and we are using base. What happened? This OCOCH will be displaced by OH. Then we are getting this product. So these are the typical acidic nature of the reactions. In all this simple concept here is the one which forms anion forms last reacts with alkyl halide or any acylation. That one is going to take part first. The anion which formed last and that one participated first. So how to react? Less reactive group means these are the ways. It will be how to react. Less reactive group has to participate in the reaction. Then by using these examples, you came to know which one is going to participate and which one is not going to participate. Boiling point of thiol and alcohol when we try to compare. In general, boiling point depending upon intermolecular forces. And we learn thoroughly intermolecular forces means first priority hydrogen bonding, second priority dipole-dipole interaction, and third priority molecular weight, right? Means based on molecular weight, London dispersion forces are van der Waals forces. Now, here, thiol CH3SH, thiol is also called mercaptans, right? So, thiol and alcohols, when we compare boiling point here, CH3SH boiling point is 6 degrees Celsius, whereas CH3OH boiling point is 65 degrees Celsius. That means at room temperature, CH3SH exists as a gas, whereas CH3OH exists as liquid. Methyl alcohol is liquid. Now, question is why? Why like that? Before going to discuss that, first you need to recollect the information. H2S boiling point is minus 60 degrees Celsius, whereas H2O boiling point is 100 degrees Celsius. H2S molecular weight is 34, whereas H2O molecular weight is 18. Even though molecular weight of H2S is more than H2O, here what happened? Boiling point is less. So here we learn reason because of presence of intermolecular hydrogen bonding in water, its boiling point increases. That means here in water, OH bond polarity is more. Being more bond polarity, obviously dipole moment, bond polarity is more. We can say hydrogen bonding is exists because of hydrogen bonding exists. There what happened? Boiling point is more. But the same hydrogen bonding we cannot expect in case of H2S because of SH bond polarity is less. That's why SH bond polarity is less. That's why its boiling point also less. So simple. The same reason here also. So what do you say here? Here also SH bond polarity is less rather than OH bond polarity. Fine. Bond polarity is less, that's why boiling point is like that. Fine. Let's come to here. Acidic nature of RSH and ROH, what do you say? Just now we discussed. SH bond polarity is less. OH bond polarity is more. In general, what do you think? OH is more acidic than SH. No. RSH boiling acidic nature is more than ROH. So experimentally, if you observe the values, pKa values of thiols are around 11, whereas alcohols are around 16 to 18. pKa, more the pKa value, less the acidic nature. Based upon that, which one is more acidic? We have to say RSH has a more acidic nature than ROH. Why? Bond polarity you only mentioned there, you explained their boiling point case, and now you are saying that again RSH has a more acidic nature than ROH. Now how do you say that? Let's come here. Here, acidic nature not only depending upon the bond polarity but also depending upon conjugate base stability. In case of RSH, after losing proton, it converts into RS minus, where negative charge is located upon large size sulfur, resultant repulsions are less and we can say stability is more. Whereas in case of alcohols, after losing proton, we are getting RO minus, being small size of oxygen. What happened? Its charge density is more and stability gets decreased. That's why RS minus is more stable than RO minus. That's why acidic nature of RSH is more than RO minus. And have you seen this reaction? RSH upon reaction to OH minus, as we know, OH minus is strong base and RSH is strong acid. So this strong base abstracts proton from that, and we are getting RS minus and H2O. Here H2O is weak acid and RS minus is weak base. Strong acid, strong base, weak acid, weak base. So if you assume that this one is a reversible reaction, forward reaction takes place more rather than backward reaction, because of forward reaction is nothing but strong acid, strong base in neutralization. That's why forward reaction takes place more. So here RS minus is what you say, strong acid conjugate weak base. So being weak base, what we are saying that in general basicity is proportional to nucleophility, but here it is contrary. Here RS minus is good nucleophile than RO minus, ROH minus. RS minus is a good nucleophilic character than RO minus or RS minus. Alcohols, as we learned in the previous session, it acts as electrophile and nucleophile. Let us see. It shows two types of electrophilic substitution. That means oxygen is going to donate electron pair. First case to electrophile with 6 electrons. Here oxygen lone pair will be given to positive charge of electrophile. Then there will be a new bond formation between oxygen and electrophile. So that positive charge will be carried by oxygen, right? Now later this OH bond is going to break and ROE plus H plus means base abstracts this proton. So in first case, what happened here? Oxygen is going to donate electron pair to electrophile. Let's come to second case. In this case, OH minus, we are using strong base. Now OH minus abstracts proton and it converts into alkoxide ion. This alkoxide ion is going to behave as a nucleophile. So in this case, how it behaves? As electrophile. Means it likes positive charge. So nucleophile. Here also it likes positive charge in nucleophile. But in first case reaction, first electrophile has to come and attack upon oxygen. Or in other words, you can say oxygen lone pair is related to electrophile positive charge. But here not like that. Not oxygen lone pair. Here alkoxide ion. Now alkoxide ion is going to participate in SN reaction. And this one replaces that X minus, and we are getting ROE and X minus. This type of reactions generally we are seeing in the preparation of ethers like Williamson synthesis, as we learned in previous session. Alkyl halides upon reaction with sodium alkoxides gives ethers. Alkyl halides upon reaction with sodium alkoxides and gives ether as a product. But in case of that, elimination reaction or elimination of products also possible. And here let us see, I am going to give example for these two reactions. In first case, I am going to use secondary alcohol. This secondary alcohol upon reaction with the sodium hydride, which is strong base. This strong base seeks a proton and it extracts a proton because of H minus is strong base then. And strong base then alkoxide ion, that's why H minus is going to extract proton from here and leaves alkoxide ion. And this alkoxide ion upon reaction with alkyl halide, upon reaction with alkyl halide, which alkyl halide is primary alkyl halide, then we are getting product here, substitution product, that is either as a final product. In first case we are using strong base. When we are using strong base, it extracts proton and it converts into alkoxide ion. Basically, alcohol likes electrophiles. Means it seeks electrophiles. They are electron rich. Upon reaction with the base, that oxygen we are going to make further more electron rich. Basically, oxygen is electron rich, but after reaction with base, furthermore electron rich alkoxide ion, that alkoxide ion is going to participate in substitution reaction. Now let us come here. In this case, isopropene. This one, upon acidification, we are getting tertiary carbocation. Now this one acts as a strong electrophile, and this one upon reaction with alcohol, let us consider cyclohexanol. This cyclohexanol acts as an electrophile. So this cyclohexanol nothing but a nucleophile. This one is going to donate electron pair to positive charge electrophile, and there will be new bond formation between oxygen and carbon, and later this OH bond is going to break and we are getting ether. So in both reactions, the product what we are getting and the mechanism how the mechanism is going to proceed, that are completely different. These two, in first case we are using strong base, later displacement reaction, whereas in second case we are using strong electrophile. So whether you are using strong base or using strong electrophile, in both cases we are getting substitution product as major product. Look this question. Primary and secondary alcohols upon oxidation we are getting carbonyl compounds, whereas in tertiary alcohols cannot undergo any oxidation. This point will end. And generally oxidizing agents we can use any. I am going to suppose use here sodium hydroxide and chlorine, that reaction well known. NaOH upon reaction with chlorine we are getting NaCl and NaOCl made sodium hypochlorite we are getting. As a hypochlorite ion is a good oxidizing agent, it can oxidize alcohols, means primary alcohols into aldehydes, secondary alcohols into ketones. Here primary and secondary alcohols upon oxidation we are getting carbonyl compounds, that reaction is familiar. But here which we should learn is tertiary alcohol. Let us consider tertiary butyl alcohol. Tertiary butyl alcohol upon reaction with chlorine in presence of NaOH, we are getting halogenation and oxygen. So halogenation and oxygen takes place, nothing but electrophilic substitution takes place at oxygen. So try to write mechanism how that proceeds. Got the question? Primary and secondary alcohols upon reaction with sodium hydroxide and chlorine, we are getting carbonyl compounds like aldehydes or ketones. Primary alcohol gives aldehydes, secondary alcohol gives ketones. Whereas tertiary alcohols upon reaction with sodium hydroxide and chlorine, we are getting product, that product is different. So we are not getting, generally oxidation do not take place, but instead of oxidation what happened here? What happened here? At oxygen, halogenation takes place. Oxyhalogenation, that's what we call. Oxyhalogenation takes place. Wow. How oxyhalogenation takes place and what mechanism generally proceeds, you have to verify. Reaction with carboxylic acid. Carboxylic acid upon reaction with alcohol in presence of mineral acid catalyst like concentrated sulfuric acid and dry HCl, we are getting ester. The formed ester has basically fruity odor, and this reaction what we call Fischer esterification. Fischer esterification is nothing but alcohols upon reaction with carboxylic acid in presence of mineral acid catalyst, we are getting carboxylic ester. So, order of reactivity of alcohols, if you observe, methyl alcohol is greater than primary, primary is greater than secondary, and secondary is greater than tertiary. This is the order of reactivity towards esterification. So, methyl alcohol is more than primary, then secondary, then tertiary. So, wherever OH bond cleavage, those reactions which takes place by breaking of OH bonds in alcohols, for all that reactions, order of reactivity of alcohols, this one only, methyl alcohol is greater than primary, is greater than secondary, is greater than tertiary. And for carboxylic acid, order of carboxylic acid towards esterification is formic acid is greater than acetic acid, acetic acid is more greater than RCH2OH, R2CH2OH. That means more the number of carbon atoms in carboxylic acid, less ease of esterification. Here let us see the mechanism how it proceeds. First, carboxylic acid say RC double bond OH upon acidification, acid medium, here C double bond group get protonated, RC double bond OH and OH. Upon this reaction, R-OH alcohol now acts as just a nucleophile, and in order to facilitate that alcohol oxygen pi electrons are shifted towards oxygen atom, then we are getting RCOH, OH, and here OR-H plus. Now, whenever this more alternative oxygen base positive charge, immediately this one gets this bonds OH bond electrons. This H plus goes to either of these two OH group, then we are getting RCOH2 plus and OH, here OR dash. Later, again, this one is going to bear positive charge, and this OH group acts as a leaving group. We are getting RC. Here this one leave, and there will be no double bond formation between carbon and oxygen. At the time, this oxygen is going to bear positive charge, and here OR dash remains. And to compensate that positive charge, OH bond electrons again shifted. Then we are getting R C double bond O R dash. This mechanism we can confirm by keeping O18 isotope, means isotope, by keeping isotope here. So which bond is going to break and which bond is not going to break, that we can understand very easily. So here generally what we are getting, there are two possibilities. By breaking RO bond of alcohol and OH bond of carboxylic acid. Generally we are expecting, because of carboxylic acid there are more tendency to donate H plus. That's why maybe we are expecting that OH bond is going to break, and in alcohol RO bond is going to break. But actually, if you observe the mechanism here, actual bond breaking takes place in between carboxylic carbon and oxygen and this OH. That means here in this reaction, dehydration will nothing but losing of water here. This dehydration, OH group from carboxylic acid and hydrogen from alcohols are going to be removed. That means here alcohols nothing but you can say show acidic property, and carboxylic acid shows basic property. Now that we came to confirm by keeping O18 isotope. Here I am going to keep RC double bond OH plus R dash O18H. So when we are using R dash O18H, this 18 O18 goes to where? For example, if R dash O bond is going to break, then obviously this O18 will comes in water. Whereas if OH bond is going to break, this O18 will appear in ester. Check out the mechanism by keeping here O18 and one more RC double bond O18H and R dash OH. In both reactions in acid medium, how they are going to perform. Now, so far we discussed that monocarboxylic acid means which consists only one COOH group. Now, this one is oxalic acid, dicarboxylic acid. Oxalic acid upon reaction with glycol, which is ethylene glycol. Here, glycol OH group and oxalic acid OH group are going to participate. Here dehydration takes place, here dehydration takes place. Resultant we are getting product like this. And in this case, here one end intramolecular esterification within the molecule. Actually, so far two different molecules, one is carboxylic acid and one is alcohol participated. In this reaction, one dicarboxylic acid and one diol is going to be participated. Now in this reaction, Within the molecule, OH terminal and COOH terminal both are there, consonant, sulfuric acid and heat. So here what happened here? Within the molecule, intramolecular esterification 1, 2, 3, 4, 5 with oxygen 6. That means there will be formation of 6-membered ring. And wherever oxygen is there, with respect to the next one, 2 methyl groups are there. So here one C double bond O. Because of C double bond O OH, let us write here C double bond O OH means this OH group and this hydrogen is going to eliminate, and C double bond O C double bond O say here C double bond O. In between these two, new bond formation takes place in between this C double bond O and this oxygen. With respect to C double bond O addition carbon pairs, 2 methyl groups. Here if you observe within the molecule again, just like this, within the molecule both carboxylic end and OH group, here intramolecular dehydration takes place. As a result, we are getting cyclic ester, that is nothing but lactone. So lactone, cyclic esters, what we call lactone. So 1, 2, 3, 4, 5 membered formation takes place. Not only carboxylic acids but also carboxylic acid derivatives are going to participate in this reaction. So acetic acid upon reaction with PCl3, we are getting acid chloride CH3 C double bond OCl, and acid chloride upon reaction with ethyl alcohol and alcohol, here nucleophilic substitution reaction, then we are getting CH3 C double bond OC2H5. This is what we call the ethyl chloride ester. Not only acid chlorides but also anhydrides. Anhydrides also here it involves in nucleophilic substitution reaction. The resultant we are getting CH3 C double bond OC2H5 plus CH3COOH. This is reaction with carboxylic acid. Reaction with carboxylic acid. Carboxylic acid upon reaction with alcohol in presence of mineral acid catalyst like concentrated sulfuric acid and dry HCl, we are getting ester. The formed ester has basically fruity odor, and this reaction what we call Fischer esterification. Fischer esterification is nothing but alcohols upon reaction with carboxylic acid in presence of mineral acid catalyst, we are getting carboxylic ester. So, order of reactivity of alcohols, if you observe, methyl alcohol is greater than primary is greater than secondary, and secondary is greater than tertiary. This is the order of reactivity towards esterification. So, methyl alcohol is more than primary, then secondary, then tertiary. So, wherever OH bond cleavage, those reactions which takes place by breaking of OH bonds in alcohols, for all that reactions, order of reactivity of alcohols, this one only. Methyl alcohol is greater than primary, is greater than secondary, is greater than tertiary. And for carboxylic acid, order of carboxylic acid towards esterification is formic acid is greater than acetic acid. Acetic acid is more greater than RCH2OH, R2CH2OH. That means more the number of carbon atoms in carboxylic acid, less is of esterification. Here let us see the mechanism how it proceeds. First, carboxylic acid say RC double bond OH upon acidification, acid medium, here C double bond group get protonated, RC double bond OH and OH. Upon this reaction, R-OH alcohol now acts as just a nucleophile, and in order to facilitate that alcohol oxygen, pi electrons are shifted towards oxygen atom, then we are getting RCOH. OH and here OR-H plus. Now whenever this more alternative oxygen bears positive charge, immediately this one gets this bonds OH bond electrons. This H plus goes to either of these two OH group, then we are getting RCOH2 plus and OH, here OR-. Later again this one is going to bear positive charge and this OH2 group acts as a leaving group. We are getting RC, here this one leave, and there will be new double bond formation between carbon and oxygen. Resultant this oxygen is going to bear positive charge, and here OR- remains. And to compensate that positive charge, OH bond electrons again shifted, then we are getting RC double bond OR-. This mechanism we can confirm by keeping O18 isotope means isotope. By keeping isotope here, so which bond is going to break and which bond is not going to break, that we can understand very easily. So here generally what we are getting, there are two possibilities. By breaking RO bond of alcohol and OH bond of carboxylic acid. Generally we are expecting, because of carboxylic acid there are more tendency to donate H plus. That's why maybe we are expecting that OH bond is going to break, and in alcohol RO bond is going to break. But actually if you observe the mechanism here, actual bond breaking takes place in between carboxylic carbon and oxygen and this OH. That means here in this reaction dehydration will nothing but losing of water here. This dehydration, OH group from carboxylic acid and hydrogen from alcohols are going to be removed. That means here alcohols nothing but you can say show acidic property and carboxylic acid shows basic property. Now that we came to confirm by keeping O18 isotope. Here I am going to keep R C double bond OH plus R dash O18H. So when we are using R dash O18H, this 18 O18 goes to where? For example, if R dash O bond is going to break, then obviously this O18 will comes in water. Whereas if OH bond is going to break, this O18 will appear in ester. Check out the mechanism by keeping here O18 and one more R C double bond O O18H and R dash OH. In both reactions in acid medium, how they are going to perform. Now, so far we discussed that monocarboxylic acid means which consists only one COOH group. Now this one is oxalic acid, dicarboxylic acid. Oxalic acid upon reaction with glycol, which is ethylene glycol. Here glycol OH group and oxalic acid OH group are going to participate. Here dehydration takes place, here dehydration takes place. As a resultant we are getting product like this. And in this case, here one had intramolecular esterification within the molecule. Actually, so far two different molecules, one is carboxylic acid and one is alcohol participated. In this reaction, one dicarboxylic acid and one diol is going to be participated. Now, in this reaction, within the molecule, OH terminal and COOH terminal both are there, constant sulfuric acid and heat. So here, what happened here? Within the molecule, intramolecular esterification 1, 2, 3, 4, 5 with oxygen 6. That means there will be formation of 6-membered ring. And wherever oxygen is there, with respect to the next one, 2 methyl groups are there. So here one C double bond O. Because of C double bond O OH, let us write here C double bond O OH means this OH group and this hydrogen is going to eliminate, and C double bond O C double bond OO, say here C double bond OO. In between these two, new bond formation takes place in between this C double bond O and this oxygen. With respect to C double bond O, addition carbon pairs, 2 methyl groups. Here, if you observe within the molecule again, just like this, within the molecule, both carboxylic and OH group, here intramolecular dehydration takes place. As a result, we are getting cyclic ester, that is nothing but lactone. So lactone, cyclic esters, what we call lactone. So 1, 2, 3, 4, 5-membered ring formation takes place. Not only carboxylic acids but also carboxylic acid derivatives are going to participate in this reaction. So acetic acid upon reaction with PCl3, we are getting acid chloride CH3 C double bond OCl, and acid chloride upon reaction with ethyl alcohol and alcohol. Here nucleophilic substitution reaction. Then we are getting CH3 C double bond OC2H5 is what we call the ethyl conjugate ester. Not only acid chlorides but also anhydrides. Anhydrides also here it involves in nucleophilic substitution reaction. The resultant we are getting CH3 C double bond OC2H5 plus CH3COOH. This is reaction with carboxylic acid.